substitution in case of uh, quinoline. Okay, so that one is a really important thing, electrophilic substitution in case of quinoline. So here I have given quinoline on electrophilic substitution. Now we have different sites for the electrophilic substitution, but before some time we have seen that pyridinyl ring is electron deficient and benzenoid ring is electron rich, as we have seen in our second or third slide. So obviously electrophilic attack, we do show attack on benzenoid ring over here. Okay, so first we will see when electrophile will attack at the fifth position. The fifth means in this position. So when electrophile at a fifth position, it leads to the two different resonating structure. Okay, so pay attention over here. And when electrophile attack at the sixth position, okay, this is sixth position, so only one resonating structure forms. See, pay attention that this structure, this pyridine ring is aromatic over here. So this aromaticity, this structure, so you can say maybe this carbon atom can shift over here, and this positive charge can shift here. But this is not possible because we cannot break this aromaticity of the pyridine ring. It becomes a fully unstable molecule, and this is not possible. It's unfavorable to disturb this aromaticity of this ring. Okay. So we have to play with when that one is attacking at sixth position. This positive charge is located only on this one, only on this fifth position. So only one resonance structure can create over here. So that one is also not forming, and they are shown here. They are less stable. Okay, so when electrophile attacks at the seventh position now, fifth, sixth, seventh, then also only one structure is forming. That one is also not forming. They have shown it's not possible. Less stable. These structures, both structures are less stable when electrophile attack at the sixth and seventh position. So less stable molecules, less stable resonance structure forms. Almost they don't form. So that's why attack at the sixth and seventh position is not possible. And now last position for attack, it's the eighth position. And when electrophile attacks or getting attack at the eighth position, the uh, what resonating two resonating structure they do form. And that's why the electrophilic attack more predominantly occurs at the fifth and eighth position. Okay, so electrophilic substitution reaction do not occur in pi deficient pyridine ring of quinoline. So pyridinyl ring is electron deficient, and as electrophile is also electron deficient. So electron deficient cannot work. So we have to search for electron rich benzenoid ring will react with the electrophile. Okay, so it becomes even more electron deficient by protonation in acidic medium. When nitrogen is getting protonated, it becomes still more electron deficient. So electrophilic attack at this pyridinyl ring is highly impossible. Next one, in acidic medium, preferentially electrophilic substitution occurs in the benzene ring. Okay, so for the electrophilic substitution reaction in quinoline ring, in benzenoid ring here, we need highly acidic medium. We need highly acidic medium, and under only highly acidic medium, not only but under highly acidic condition, quinoline get electrophilic substitution at fifth and eighth position. Okay, so these two positions, fifth and eighth position, they are susceptible for electrophilic substitution reaction in quinoline. So here I have given benzene is more electron rich than pyridine. So that's why electrophile will try to go at benzene ring, benzenoid ring. At low acidic strength, electrophilic substitution may occur in the third position of the pyridine ring. Okay, so we'll see now at low acidic strength how the electrophilic substitution occurs in the pyridine ring. Now some explanation I have given here. It is clear that attack at position 8 or 5 is two more stable resonance structure in which the aromatic sextet of the pyridine ring is preserved. Okay, so what I have told that we are not we have to take care of the aromatic sextet of the pyridine ring. We shouldn't have to disturb that aromatic sextet of pyridine ring. We have to preserve that aromatic sextet of pyridine ring, so then only that molecule is stable. If we will disturb that pyridine ring, then the molecule is no more in quinoline form. So while at attack at position 6 or 7 yields only one structures only in which the aromatic state is preserved. Position 8 is preferred than position 5 due to the less stability of the resonance structure A in comparison to B. Other resonance structures are unimportant. They are particularly unstable because the aromatic state is disrupted. Okay. So summary is the electron substitution occurs at 8th or 5th position, not in pyridinyl ring but in benzenoid ring. Okay, next one, regioselectivity in case of electrophilic substitution. So occurs at C5 and C8 here. They have given here. Preferentially, it will go for the 8th position. Normally, it's a star they have given. So it goes at the 8th position rather than the 5th position. So isoelectronic naphthalene also undergoes 1st, 4th, 5th and 8th position. Next, under strong acid, why we need this acidic conditions for the electrode substitution? Once we will do the reaction of quinoline under acidic condition, this nitrogen is getting protonated. That we know lone pair which is present on nitrogen atom is free to abstract the any proton or anything. So once that lone pair is getting utilized, this pyridine ring again becomes more electron deficient. Okay, so that one is becomes more electron deficient. Then the selectivity or regiochemistry of the electrophilic substitution occurs. The chances of this regiochemistry or regioselectivity get increased, and the electrophilic substitution occurs predominantly only in benzenoid ring. Okay, so whatever 2 to 5% chances of electrophilic substitution in pyridinyl ring was there, it was also getting finished once nitrogen is getting protonated. Okay, so this after protonation of this nitrogen, this pyridine ring becomes more electron deficient, and there is no possibility at all of electrophile will go in this pyridine ring. Okay, that's why we need strong acidic conditions for the electrophilic substitution in case of quinoline as well as isoquinoline. So attack occurs at the benzo rather than the hetero ring. Reactions are faster than those pyridine but slower than those of naphthalene. So this is the overall situation or scene for the electrophilic substitution in case of quinoline ring. Okay, now we'll see how the reactivity of the electrophilic substitution reaction. So electron substitution occurs via addition elimination, in the benzenoid ring, more electron rich ring. So reactivity, reactive towards the many electrophiles. It is less reactive than benzene, but quinoline is more reactive than pyridine. Here I have given relative rates of the reactivity. Quinoline ring is here. So quinoline ring is less reactive, relative rate of, okay, this is standard rate of benzene ring. Okay, so if benzene relative rate is 1, so for electrophilic substitution, in quinoline electrophilic substitution rate is 10 raised to minus 6, is far lower than this 1. Okay, so for in case of electrophilic substitution reaction, it's less reactive than benzene, but it's more reactive than the pyridine ring. Okay, regioselectivity we have seen. Substitution at C5 and C8, okay, occurs, predominates via more stable Wieland intermediates. Okay, so C5, C8, they are more important. Okay, we'll see now nitration of this quinoline ring. So quinoline, as I have told that we need strong acidic condition. So strong acidic condition HNO3, H2SO4, 25 degrees centigrade. Nitration goes 43% product we got at 5th position nitration, and 47% product nitration product we got at the 8th position. Okay, so this is the ratio of the nitration. Next reactions, bromination reaction. Okay, electrophilic. Under conditions of high acidity, bromination occurs normally at position 5th and 8th. Okay, so the main product is the 8 bromo quinoline. When bromination we do conduct in presence of strong acidic condition, H plus is important over here. So main product is 8 bromo quinoline, and minor product is the 5 bromo quinoline. However, vapor bromination, which is carried out under drastic conditions, result in bromination of the less reactive pyridine ring to yield 3 bromo quinoline. This is comparable to the bromination of pyridine to use 3-bromopyridine. So here we didn't use the acidic condition H plus, and under vapor bromination we can get the 3-bromoquinoline. Okay, so this is also one process. So pay attention at the reagents what they have given on this arrow. Next one, some data from the Gilchrist book I have taken here. Electrophilic substitution occurs preferentially at 5th and 8th positions or both. Okay, so table 5.4, electrophilic substitution of quinoline and isoquinoline. So electrophiles they have given. In case of quinoline, I have given not isoquinoline, only quinoline. So deuteration, nitration, bromination, and sulfonation. So reagent and conditions I have given. Nitration H2SO separation of 0 degrees centigrade. 5th and 8th position, 1:1 product you can get. Bromination Br2 AlCl3 Lewis acid catalyst 80 degrees centigrade, only 5 bromo quinoline you can get. Sulfonation, see reagents are different here. For bromination they have used AlCl3 and 80 degrees centigrade. On previous one Br2 in H plus they have taken, we got the 8 bromo as a major product. Okay, so pay attention at the reagents and conditions of the reaction. Sulfonation reaction. Sulfonation reaction they have carried out with H2SO4, SO3 at 90 degrees centigrade. So at position sulfonation occurs as a major product. These are the some reactions of the electrophilic substitution reaction. Now this one is the nitration of the quinoline, how that one is takes place at the third position in pyridinyl ring. So at low acidic strength, okay, so here is acidic strength is lower. They have used only nitric acid and acetic anhydride. So this is low acidic strength. Substitution may observed in the pyridine ring at position third. Okay, so formation of N oxide of quinoline activates pyridine ring. Okay, N oxide quinoline. So here is the oxide, oxygen is getting attached at nitrogen atom to form the N oxide. Nitrogen possesses positive charge, oxygen possesses negative charge. So in that case, in N oxide, when N oxide is there in case of quinoline, so at that time towards electrophilic reagents in case of pyridine. So at that time with N oxide in here, so electrophilic substitution occurs at the fourth position in pyridine ring. So quinoline N oxide may therefore be substituted by electrophilic reagents in pyridine ring. Okay. So reactivity pattern of quinoline is different and quinoline N oxide is different. So next one, oxidation reaction of the quinoline. So quinoline is stable compound resistant to oxidizing agents, but vigorous oxidation with potassium permanganate yields quinoline acid. Okay, quinolinic acid we can say, alpha beta pyridine dicarboxylic acid. So this ring is getting destruct and getting open. Okay, or we can say this ring is benzenoid ring is getting oxidized, and we can get the quinolinic acid. Okay, so alpha beta pyridine dicarboxylic acid we get. So benzenoid ring undergoes oxidation, that one is getting open, and we can get this type of oxidized product. Preferential oxidation of benzene ring has been explained by its comparative lower stability than the pyridine ring. So benzenoid ring, stability of benzenoid ring is less than the pyridine ring. That's why this benzenoid ring or benzene ring is getting oxidized, and we do get this pyridine alpha beta dicarboxylic acid. Next one, reduction reaction of the quinoline. So pyridine ring is more easily reduced. See, in oxidation, benzenoid ring is getting utilized or getting oxidized, and now in case of reduction, pyridine ring is getting reduced easily than the benzene ring. Thus, the catalytic reduction of quinoline yields 1, 2, 3, 4 tetrahydroquinoline. So in reduction, pyridine ring is getting reduced. This 2 double bond is getting reduced by in presence of hydrogenation in raninical hydrogenation reaction. Complete reduction we can observe to decahydroquinone is comparatively more difficult and is achieved by using platinum catalyst in acetic acid. So complete reduction decahydroquinone we can get by the catalytic reduction in platinum containing catalytic reduction in presence of acetic acid. So these are the some examples of the our electrophilic substitution reaction, and in next thing we will cover our nucleophilic substitution reaction as well as synthetic synthesis of the quinoline 3.